Hi everyone, this is going to be a walkthrough video of problem 7 on CS61B, Spring 2021 Midterm 2. So, in problem 7, we are given three functions and we're trying to figure out the best and worst case runtime of each function. So, for the first problem, we're trying to figure out what's the best and worst case runtime of this alpha function here. Okay? So before we dive in, I want to give you guys a bit of intuition on how you guys can approach these similar problems in the future. So when we think about the best case, what we're trying to do here is we're trying to figure out what will cause our function to exit as quickly as possible. Okay, so the best case runtime is that our function exits as fast as possible, right? The best case means that we're spending the least amount of time, which means our function should exit as fast as possible, right? So in a symmetric fashion, we can kind of think about the worst case as what will cause our function to exit as slowly as possible, okay? So this is the main difference between best and worst case, okay? And this intuition, I think, is really valuable when we approach these best and worst case runtime problems. So coming back to alpha, what we can say is that in the best case, our function alpha will have a number that is even. Okay, let me quickly expand on why this is the case. Looking at this function, we want the best case to be when our function exits as fast as possible. The first time we see a return is right here. So for our function to exit as fast as possible, we want to hit this return, right? In order to hit this return, it means that n must be even, right? In other words, n mod 2 must be equal to 0. So in the best case runtime of alpha n, the number that we are given is even, in which case we hit this return and we've performed a constant amount of work. So what we can say is the best case runtime of alpha n is going to be theta of 1. Okay? So let's move on to the worst case. Recall our worst case is what will cause our function to exit as slowly as possible, right? This is called worst case behavior. So let's kind of move this to the side so that we remember it exists but it doesn't take up the space. And let's dive in to this function. How I'm going to approach it is, let's ignore this, okay? I'll explain why this is the case later, but for simplicity, let's ignore that second call to h. Now what I'm going to do is I'm going to create a little table here, okay? So for every value of I, we issue one call to h of I, right? So what I'm going to say is here in the first row is going to be the values of I. In the second row is going to be the amount of work h of I does for that value of I, okay? If this doesn't make sense, let's walk through it. So when I is equal to 1, we call h of 1, right? H of 1 runs in linear time, so this says h of 1 will take 1 time, okay? Now, when I is equal to 2, we call h of 2, right? H is linear, so this is 2 time, okay? Now, what we can kind of see here is that when I is equal to 4, we call h of 4. This takes 4 time, so we kind of have the following table, where this pattern repeats until I is equal to n, and then each value of I, we perform h of I work, which means that this column looks like so, okay? So another way of thinking about this column is that this is the work we do for every value of I. Okay, so what do I mean by that? And there's this idea called work, and I like to characterize work as the amount of steps something takes. Okay, so work is the same thing as saying a number of steps a function goes for. And another way of thinking about asymptotic analysis, as we are trying to figure out the total work a function does. Okay, bringing this all back, looking at this column h of I, we can see that this column represents the total amount of work our function alpha is doing, right? So what we can say is that in order to figure out the runtime of our function, all we need to do is figure out the sum of this column. Well, what is the sum of this column? Well, the sum of this column can be rewritten as 1 plus 2 plus 4 plus 8, right? 8 would be the next number, plus n. Okay? Now this comes out to theta of n, and it should be a sum that you all are familiar with just from discussion or from lecture, okay? So what we can say is that if we ignore the second call to h of I, we will have the following table result, which tells us the total amount of work our function is doing is theta of n. So now let's imagine that this second call existed, okay? I'm going to argue that if the second call existed, even if h of I always was true, we're not going to change the worst case runtime at all, okay? The reason is that we can kind of think about this extra call to h of I, all it's doing is doubling the total work, right? Imagine that now we have all of this extra red work added. What we can see is that all this is doing is adding another theta of n work. Asymptotically, if we have theta of n work and another theta of n work, we still asymptotically theta of n, right? So what we can say is that we can really just even ignore the second call to h of I. It doesn't really change the runtime asymptotically. So finally, let's put in the values of theta of 1 for best case and theta of n for worst case. Nice. Moving on to the next part, now we're going to be approaching the best and worst case runtime of beta, which is given as below. Okay, well, let's first try to approach the best case runtime. When we approach the best case runtime, we're trying to figure out when does our function exit as fast as possible? Well, the first time we have a return is right here, is the first return, right? So what we can say in the best case runtime, this h of n is true, and we immediately hit this return and exit, which means that the total amount of work our function executes in the best case is h of n, right? So let's put that here. In the best case, we perform theta of n work, and this theta of n stems from h of n, right? Because in the best case, we run h of n, that evaluates to true, we return, and all we've really done is just call h of n. So let's approach the worst case. So in the worst case, we take as much time as possible, which means we're not going to hit this return, right? Which means that h of n is going to evaluate to false, and we're going to go to this for loop, okay? So in the worst case runtime, we've already performed n work because of h of n, right? So let's try to figure out the total amount of work that we're doing in this for loop, right? Let's find how long this takes, right? Which is my way of saying, let's figure out the work done, okay? So how I like to approach these nested for loop problems is with the same chart I drew from the previous problem. So for every value of I, let's ask ourselves how much work are we doing for that value of I, okay? I'm going to characterize work as how many steps, it's how many steps the inner for loop runs for. Okay, so that's like what my definition of work is, and that's like my usual definition of work, nothing new. Okay, so let's walk through the first few values of I and try to see a pattern. When I is equal to 1, what will happen is that j will be equal to n minus 1, right? So if we look at how j changes, j will start at n minus 1, right? J will then become n, and then we will exit. So the number of times we've executed this int a line is 1 time. So what we can say is that the total number of steps this for loop goes for is 1, which means the total amount of work we do when I is equal to 1 is 1 work. Well, let's approach the next value of I. When I is equal to 2, j is going to be equal to n minus 2. What we see is that j will be equal to n minus 2, then j will be equal to n minus 1, j will be equal to n, and we will exit the inner for loop, which implies that we executed this line 2 times, which means that the total amount of work we do when I is equal to 2 is 2 work. Let's do one more iteration, and then I think the pattern will crystallize. When I is equal to 4, j is equal to n minus 4. Then j will be equal to n minus 3, then n minus 2, then n minus 1, and then n, and then we're done with the inner for loop. So what we can see here is that for these 4 times, we execute this line. So what we can say is when I is equal to 4, we perform 4 work, right? And now I think we've seen the pattern, is that I will get multiplied by 2 every time until it becomes n. And the amount of work we do for each value of I is proportional to that value of I. When I is 4, we do 4 work, right? So what we can say is for any value of I, we're going to be doing I work, right? And then what we can say is that ultimately, when we get to n, the last time we'll be performing like around n work, right? So looking at this column, we see it's the exact same as the column from the previous problem, right? And what we can conclude here is that this is simply the sum of 1 plus 2 plus 4 plus 8 plus n. In other words, it's going to be theta of n, right? And now what we've noticed is that in the worst case, we perform n work for h of n, and then we perform n work for this inner for loop stuff, or the whole for loop area, right? So we can see that the worst case runtime is just theta of n, the same as the best case, because this for loop didn't really add anything asymptotically. And then this if thing at the bottom is just kind of pointless. So what we see is that this is theta of n in the best and worst case. Okay, we're almost there. Let's walk through gamma. So for this problem, we're assuming f of n returns a random number between 1 and n over 2 inclusive, and does so in constant time. Okay, so what we have here is we have some for loop where I starts off at f of n. For every value of I, we issue a call to gamma of I, and I is incremented by f of n each time. So this problem may seem a bit intimidating to approach. So what we want to remember is when we approach the best case behavior, when we approach the worst case behavior, we do so using these two ideas. I kind of want to bring this back because I think it's really important. Is that, oh man, I went a little too far. Okay, so the idea here is that in the best case, we're trying to figure out what causes our function to exit as quickly as possible. And then the opposite is true for the worst case. So for our function to exit as quickly as possible, that means that we perform the fewest number of steps in this for loop, right? So what I'm trying to say is that in the best case, our function takes as little time as possible, right? For our function to take as little time as possible, we probably want to spend the least amount of time in this for loop, right? We don't want to spend that long in the for loop. We want to get to the end quickly. In order to get to the end quickly, it means that we start at a high value of f of n, right? So this value is as high as possible. And then our step size, how much I changes each time, should also be as high as possible in order to exit this for loop as quickly as possible, right? Well, the biggest number f of n returns is n over 2. So in the best case, let's assume that f of n will always give us n over 2. Okay, so how I'm going to rewrite the problem in the best case is I is going to be equal to n over 2, and then I is going to be plus equals n over 2, because we want our function to be as fast as possible. So coming back to this for loop, what we can see is that regardless, we will always call gamma of n over 2, right? Because that's the first call. Then what we're going to do is say I plus equals n over 2. Well, this could have another function call, right? Let's say that n is equal to 7. What will happen using integer math is that I will be equal to n over 2, which is equal to 7 over 2, which is equal to 3 using integer math. So what we can say here is that I starts off at 3, then we do I plus equals n over 2, and then I becomes 6, in which case we call gamma of n over 2, and then we also call gamma of n minus 1, right? Well, this is so bad because gamma of n minus 1 is a huge call to gamma. So let's think about it. If n is even, do we have this extra call to gamma? Well, let's see. If n is even, let's just say n is 8. What will happen is that I will start off as 4. Then we do I plus equals n over 2. Then I will be equal to 8. So this won't be true. And all we've done is one call to gamma, right? All we've done is call gamma of n over 2. So can we assume in the best case behavior that n will always be even, right? So let's just assume that, because we can. That's how best case behavior works. What will cause our function to exit as quickly as possible? Well, let's say n is even. And for n to be even, every time we call gamma, it means that n must be a power of 2. Okay? So let me repeat that because it's very important. My conclusion I made is that when n is even, we only issue one call recursively, right? Well, that recursive call is going to be of n over 2. So the second time, it'll be n is equal to 4. Well, can we ensure that the second time we call gamma, the new value of n is still even, right? And a broader claim is, how can we assure that every time we call gamma, repeating n divided by 2, then n divided by 4, n divided by 8, that for each value here, n is going to be even, right? How is that possible? Well, that is only possible if n is initially a power of 2, okay? So bringing this all together, in this best case situation, we're going to assume two things. We're going to assume that f of n always spits out n over 2, and we're going to assume n is a power of 2, okay? Using both of these assumptions, I'm going to draw out how our recursive tree will look, okay? So just buying myself a little space. Looking at the recursive tree, we're going to have an initial call of input size n, right, to gamma. And how much work are we going to be doing to the first time we call gamma? We're going to be doing 1 work. Then assuming n is a power of 2, we will only call gamma once with input size n over 2, right? And what we can see here is that we will have this following tree, right? Where the value of n gets decremented or gets halved every time. And at the bottom, we have a 1 node, right? So the total amount of work we're doing is the sum of the work for each time we call gamma, right? And just to recap, inside of this little node is the work, and then the top is the input size. So we can see here that the total amount of work we're going to be doing is the total amount of these ones. Well, how many ones are there? The total amount of ones is proportional to the height of this tree. Since we divide n by 2 every time, we see the height of this tree is log n, which means that the total amount of work we're doing in the best case is log n, right? Cool. So I'm going to temporarily remove all of the stuff we did. And let's approach the worst case. So I think the worst case, what we can see here is that we're going to call gamma a ton of times. And for this walkthrough video, I want to be very, very clear, and I'm actually going to calculate the worst case runtime for gamma of n. So this problem has an upper bound, and we'll soon realize that we're going to be executing much more work than n to the 4th log n. So let's try to figure out the exact amount of work that is, just for whoever's watching, you guys to really understand asymptotic analysis. And I think it's a lot more fun to try to figure out the exact amount of work we do in the worst case, right? Well, in the worst case behavior, let's make a couple assumptions. Actually, let's just make one assumption, that f of n is always going to return 1, okay? So my idea here, why I'm making this assumption, is our worst case runtime should be as much work as possible. We should be going as slowly as possible, and we should be issuing as many recursive calls as possible. What this implies is that f of n should always give us 1, so then we keep calling gamma recursively, right? Now, let's directly look at the corresponding recursive tree. I think this is really cool. So, looking at this corresponding recursive tree, the first time we call this function, the input size will be n. This is the input size. And the amount of work we're going to be doing, well, this is kind of tricky, right? How much work are we really doing here? Well, let's see. So all we're actually doing in the gamma function is we have a base case, and then we're just issuing recursive calls. So we're not actually doing any work in the gamma function, right? We have a base case, we're issuing recursive calls. So what we can say is that gamma actually runs in constant time and then issues n recursive calls, okay? So what I'm going to say is that we do a constant amount of work. Equivalently, we can also put n here. This is also valid since we do perform n work during our n-1 recursive calls, but you'll see that the same runtime comes out of it. Okay, so now what I'm going to do is looking at this for loop, when f of n always gives us 1, this is really how it looks. So we're going to be calling gamma of 1, then gamma of 2, gamma of 3, gamma of 4, all the way up to gamma of n-1. Okay, well, that's so many recursive calls. Let's kind of look at it. So we're going to be calling gamma of 1, Then we're going to be calling gamma of 2 all the way up till, I'm going to move this down a bit. Right? All the way, there's so many more here to gamma of n minus 1. Okay? So we already have this many recursive calls. Okay? Now, what I'm going to notice is that let's just only look at this next recursive call, the next biggest one to n minus 1. Okay? And believe it or not, we're actually going to see a really cool sum up here. So to recap what I've done so far is I've noticed that if f of n always gives us 1, then what will happen is that our function gamma of n will issue the following recursive calls. Gamma of 1, then gamma of 2, all the way up till gamma of n minus 1. And then I've represented each of these as such, right? Okay, so hopefully that was a good explanation of just like what I'm really drawing here. Now what I'm going to do is only consider the top one, okay? Looking at gamma of n minus 1, what we can realize, it's going to do a very similar thing that gamma of n did, okay? What will happen here is that gamma of n minus 1 will, let me try to improve my drawing skills. We're going to assume these people are a little lower on the tree. So gamma of n minus 1, well, we already had a call to n minus 2, right? Let's just add that one in from the first time we called gamma of n. So looking at gamma of n minus 1, what we're going to be doing is that we issue another call to n minus 2, right? And we really issue a bunch of calls all the way from n minus 2 all the way down to 1, okay? So let me just zoom in a bit. So what we've done so far is, if we're looking at the first time we call gamma, this is gamma of n. This is going to issue the corresponding recursive calls, okay? Then what I'm going to do is I'm going to consider gamma of n minus 1, right? Gamma of n minus 1 is going to issue all of these calls, right? All the way from n minus 2 all the way down to the bottom, okay? And there's all of the calls here. So now what I'm going to do next is I'm going to consider gamma of n minus 2. So considering gamma of n minus 2, what will happen is that we will have another layer here. Let me get a little more space. Okay, so let's imagine that we have the next layer just added to the tree. It already existed. I'm just adding it back to the tree. So here we're going to have the calls to n minus 3. I'm just adding them back to the tree. Okay. So now what's going to happen is when we look at gamma of n minus 2, we're looking at, to be precise, this call right here. Okay. What's going to happen for this orange call is that it will issue the series of calls from n minus 3 all the way down to 1. Okay. So gamma of n minus 2 will issue these orange recursive calls, right? And then what we'll notice is that we have two calls to gamma of n minus 2, right? Which means that if we're looking at this call to gamma of n minus 2, we will also issue the same number of recursive calls, right? We'll just call these ones the red ones. And what we can see here, which is pretty cool, hopefully you guys can kind of see what's happening, is that this first layer, we're figuring out at, these are the layers, right? At the n minus 1 layer, we're doing one work, right? At the next layer of our tree, notice that we're doing 2 work. And just to be a little more concrete, this is the work per level. Okay, so at the n-1 level, we're doing 1 work. At the n-2 level, we're doing 2 work. At this next level, we're doing 4 work, right? At the n-3 level. So let's look at another level of this tree, and I think it'll be really, really clear what's happening. Okay, so looking at each of these calls, I'm running out of colors. Looking at each of these calls to gamma of n-3, right? We know that each of these calls will issue their own series of recursive calls coming from n-4 all the way down to 1. So in essence, what we can see here is that we will have a bunch of new calls all the way from n-4 all the way down to 1, right? And then we can see this is repeated 4 times. Okay, so what we can see here is that we already had all of these calls to n-4, and then now we're doubling the total amount of calls we had to n-4, right? So what we can kind of see is that the work per level, right, is doubling each time because of this pattern, right? So what we can say is that the work at the first level is 1. The work at the next level is 2. The work at the next level is 4, and so on, right? So we get the following sum of 1 plus 2 plus 4 plus, looking at this n-4 level, this is 8 plus, well, where does it end? Well, what is the height? What is the height of this tree? Right? What is this height? The height of this tree is going to be 2 to the n, right? Oh, I'm so silly. That was so bad. The height of this tree is n, right? Because it's 1 to n, which means that the last term in this sum is going to be 2 to the n. How did I get 2 to the n? Well, notice that every time we go down a level, we double the amount of work. So if we're going down height levels, that means we've doubled the amount of work n times, which means the total amount of work we're doing at the bottom level is 2 to the n. Okay, so we're almost there. The total work we're doing is 1 plus 2 plus 4 plus 8, all the way up till 2 to the n. And we know that this sum is dominated by the last term, 2 to the n, and that is the runtime in the worst case, which sadly isn't any of these answer choices. So we'll just put n to the 4th log n, but then take pride in knowing that we figured out the runtime for sure. Well, that is all for this problem. I'll see you guys in the next one, and I hope you guys enjoyed this walkthrough.